I'd like to talk about what is called the multipole expansion of the electric potential. You remember that when we had charge distributions that had high symmetry, we were able to use the equations derived from Coulomb's law and Gauss's law to get the E fields and potentials. So here we derived a generalized potential equation. Here we took the Gauss's law and determined the E field from which we could get the potential by integrating from some reference point. We could also solve Laplace's equation or Poisson's equation, or the two together, using boundary conditions. And these boundary conditions can include the charge distribution itself. While these are challenging, and sometimes they give us more information about V and E than we really need, we're going to look at another approach that uses a series expansion from our generalized Coulomb's law. Here's our potential given by something that looks like kq over r. So remember that this involves a charge distribution that's defined within a volume tau prime. This quantity here is the magnitude of the funny vector, and the funny vector was r minus r prime. This would be the source point, this would be the field point. The multipole expansion is an approximate potential that's valid at large distances away from the charge distribution. It yields terms we can identify as monopole, dipole, quadrupole, and so on. And we can generate the E field, also term by term, using the gradient. Well, in terms of approximation, remember when we formed the potential of a dipole, we also made approximations. And actually, if we go through this again, it'll set us up to see what we do for the multipole expansion. So remember, the potential of a dipole would be the sum of the potentials of both charges, and those are given by kq over 1 over funny r plus, and so that's the distance away from the plus charge to our field point, minus 1 over r minus, and r minus is the distance from minus q to the field point. And you'll notice that the way this is set up with the plus and minus charge, this minus sign is associated with that minus sign there for the minus q. So to begin with, we form the expression for r plus, funny r plus, in terms of the r and d and the theta by using the law of cosines. And we have to be very careful in how we set this one up and this one up. But when we do, what we see is a difference of sign. So there's a minus sign here and a plus sign here. These are exact. Well, what it's going to lead to is a potential that looks like this. It's going to have a QD factor here, which remember is the dipole moment. It's going to have r squared, which is the square of this distance right here. And it's a scalar, so there's no vector associated with that. Before showing that, I'd like to just comment on the fact that if we have a monopole, which is a single charge, the potential falls as 1 over r. Here we see this 1 over r squared. Well, that's associated with a dipole. If we go to the quadrupole, it goes as 1 over r cubed. This is an example of one type of quadrupole. And if we go to an octupole, it goes as 1 over r to the 4th, and so on. One thing you'll notice that if the terms are non-zero, as r increases, the winners are in this order. So if you go far enough away, because this is 1 over r, the monopole, if it exists, is the dominant term. If you have both of these, then eventually the monopole will win. If you add more and more terms, if you go far enough away, the dominant term will be at the smallest order. So going back to our dipole calculation, we put in our funny r's so that we get the potential of the dipole, kq. This is 1 over the funny r plus. This is 1 over funny r minus. We want to expand those, but we need a factor which is either large or small, and we're going to choose one that's small. So what we'll do is, first of all, factor out an r from this square root. So r is outside, and we replace r squared with 1, and so on. So this is the removal of r in both of those factors. Now we're going to define a alpha minus and an alpha plus associated with this quantity right here. If we take our alpha minus, that will be this quantity here, which corresponds to these two terms here. Alpha plus will be these two terms, which is these two terms here. And then notice that then these factors are raised to the 1/2 power, like that. So both of these fractions are the form of 1 plus alpha to the minus 1/2, where this is either alpha minus or alpha plus. For r much larger than d, which is the case that we're interested in, alpha is small because it has in it 1 over r's. We can expand this quantity right here. We can form a Taylor series or a Maclaurin series about alpha equals 0. So we'll expand that and we'll keep a few terms. And here's the Mathematica version of that. It's just taking a series of this quantity right here about 0, and we're only going to take me up to alpha squared. So here's the expansion. It's very simple, and realize that it's approximation for 1 plus alpha to the minus 1/2. And so if we put alpha minus or alpha plus, we can get the two fractions. Well, here's alpha plus, just the way we defined it. Here's alpha minus, and we're going to take a look at this series where we now change alpha to alpha plus or change alpha to alpha minus. And that'll give us the two fractions. This will be the series plus, this is the series minus. So evaluating that, this right here is the top one. That's this quantity right here. This one right here is the bottom one, so this is associated with the minus sign. Let me just remind you what that is. Here's our exact solution right here for the dipole. And if we take these two quantities, this right here expands into this. This right here expands into this. Now this is 1 over something. These are not 1 over, but realize this quantity right here represents everything that's in the circle. And likewise for here, everything in the circle. So now we formed the approximate dipole potential by just taking the difference between those two quantities and multiply by kq over r. So just brute force, here's the difference right here, and here's our kq, and I put this r I put inside. So we have these two terms right here. For r much larger than d, we're justified in just dropping this term because it's going to be quite a bit smaller than this term. So when we do that, this is the dipole potential, which we showed on an earlier slide, and it goes as 1 over r squared. Well, you notice that we have the QD here, so we can substitute in P, which is the dipole moment, and so we're left with the potential being K P cosine theta over r squared. And remember that P dot unit vector r will give us the cosine theta, so we can replace that like this. Now we derive this in polar coordinates. This is the equation we end up with. This is independent of coordinate system. So you could use this in Cartesian or any other coordinate system. So just to remind you then, here's the potential, and this holds for r much larger than d. So let's find the electric field of a dipole from the potential we just derived. And for simplicity, we're going to stay in 2 dimensions. So we have here the potential that we just derived, and we find the E field by taking the minus the gradient. And we're going to do this in polar coordinates. Here we have the r component of E, which is equal to the first derivative of our potential with respect to r. That's this quantity here. Our theta component of E is given by this operator here operating on V, and we get kp sine theta r cubed. Well, we've seen what that looks like before. If we have a physical dipole, what that means is that the distance between them, this d, is finite. And you can see that it is open. You can actually see field lines between the two charges. If we go to a pure dipole, which is actually what these equations represent, we get this field right here. So what we do here to get a pure dipole is we keep little p constant, but we let d go to 0. So q keeps increasing as we decrease the distance. It still comes to a finite value p, and this is what the field looks like. Okay, so now let's go on to the multipole expansion. And this is going to look similar to the dipole, except we're going to have a more general charge distribution. So imagine that you have a charge distribution given in this volume here. Just to make you realize what I'm talking about, here's a sphere radius capital R, and that contains all the charge. So if we go far enough away where this length here is much larger than R, then we will have a condition that will be useful for this multipole expansion. So we put our origin near or inside of this distribution so that at R prime, as we move R prime around throughout the volume, this will be much shorter than the length of R from the origin to the field point. Theta prime or theta, we'll probably use theta, is the angle between R prime and R. So that's a little bit different than the polar angle. This is the angle between the two vectors, R prime and R. So we start with our potential. This is the general Coulomb-derived potential. And we're going to expand this. It's going to be the 1 over funny R that's going to be the thing that we expand. So this funny R and this funny R are the same. Here's the square of that funny R. The length of it is equal to R squared plus R prime squared minus 2R prime cosine theta. And that's basically using this triangle right here and applying the law of cosine. Well, we'll factor out an R squared, and so we'll get this term right here. And we're going to use the same technique where this quantity right here we're going to use as a additional or a small increment, because realize this is small. R prime is much smaller than R. So that's what we're going to call epsilon. And since this is squared, if we take the square root, this would be R times the square root of 1 plus epsilon. Put in epsilon here, take the square root of both sides, and we would end up with this relationship. So we take the inverse, 1 over R, and we have 1 over R times this quantity here raised to the 1/2 power. And then we just do the expansion. So we have 1 over R times 1 over this. This expands into this series right here. Don't forget what epsilon is. It's this quantity here. So when we put that in, this is what we have for 1 over funny R. And we just see that it has powers of R prime over R, which we can group. So when we do that, we have 1 over R, we still have the 1, then we have the factor of R prime over R being cosine theta, and so on, and so on. And you may see that these are very similar or equal to the Legendre polynomials. So identifying, for example, this would be P0, this would be P1, this would be P2, and so on. We can write the 1 over R in general as this quantity right here. For R much greater than R prime, we only need a few terms. This is exact, by the way, if we let it go to infinity. So here's what we got. Here's what we want to expand. And so we put this quantity right in here for 1 over R. And that's what we have here. So notice there's an integral, and we have our 1 over n plus 1 because we take this R outside. Well, just take a few terms. We've got this infinite series, and so the first term is just simply rho of R prime d tau. There's no R dependence other than the 1 over R out here. If you look at that, that is the total charge that is associated with the charge distribution. The next term is the cosine term, and so if you look at that, that's going to be equal to our dipole term because it has the 1 over R squared dependence. The next term is the quadrupole term, and we can keep going. There's an octupole and a hexadecapole and so on. They get very, very small as you go out into those higher orders. Well, let's look at the monopole term. So what I said before, this is just the charge density. This is all contained within the tau minus. We just end up with the total charge. So the integral is equal to Q, and that's the net total charge of this blob defined by tau prime, and that's where rho is non-zero. So we can call Q the monopole moment of the charge distribution. We don't normally do that, but that's what we could do. It has, of course, units of coulombs. So V monopole is equal to kq over r, which is consistent with a point charge at the origin. The dipole term is equal to this quantity right here, and we note that r hat dot r prime is equal to r prime times the cosine of theta. Remember, theta is the angle between these two vectors. So writing that like we just said, here's r hat dotted into r prime. We can take the r hat out because it's not dependent on the prime variables. So we assign this integral right here, to the vector p. The dipole moment of the charge distribution is equal to this quantity here. This is the dipole moment of the charge distribution, which could have other moments besides the dipole. And of course, the dipole has units of charge times distance. Writing it out in terms of a dipole moment p, it looks just like what we had before, where now this, instead of a dipole moment due to 2 point charges, is this integral over here. If you properly massage the equation for the v's, particular moments, they consist of an r-dependent factor and a quantity with no r or r prime dependence. We have then in the v dipole, the latter is the vector p. In v monopole, the latter was q. So most often we invert the order of the r prime and p dot to give us this one. This was the exact form that we had before. The quadruple term is quite complicated. It has the Legendre polynomial here. It has r prime squared here. And then the r dependence is outside, is 1 over r cubed. So it falls faster than the dipole and of course the monopole. This is harder to use. If we have a fairly simple row of r prime, then we can do this integral and everybody's happy, but it's pretty rare that you have that. In general, the electric quadrupole moment is a second-rank tensor. It has units of charge per meter squared, and as we see here, it falls as 1 over r cubed. So let's depart from this integral definition of the quadrupole term in the multipole expansion and look at a simpler charge distribution, namely 3 point charges, and find v quad from scratch, and you'll see what I mean by that. The quadrupole that I have in mind then is what is known as a linear quadrupole, and it's formed by plus q separated by distances s from a central charge of minus 2q. Here's our field point. We're going to calculate the potential just due to these 3 charges. One thing I want you to notice is that if we add the charges, we get 0. P total is 0 also, because if you look at this one, we could have a dipole pointing up with minus q plus q, and then another one pointing down, minus q plus q. 2 opposing dipoles will give you 0 total dipole. So this has no monopole, has no dipole, but let's see if it has a quadrupole. So we first are going to just treat the 2 positive charges. So we're going to take these 2 positive charges and find the potential due to those. Think of that as a dipole, except both charges are the same. So the approximations we use for the potential can be expressed in a very similar way, where r plus up is this distance, and then r plus down corresponds to this one right here. And the plus just means that it's plus charge, plus charge. This is up, this is down, just in the figure. So we have then our expression, and we can use our triangles again. They're precisely the same triangles that we had before for the dipole, and so we end up with these expressions here, 1 over the distances that we're interested in. So here it is again. We factor out an r, so we have this expression here, and then we identify these quantities right here, this one right here, with an alpha minus, and this one right here with an alpha plus. So again, it's following the same procedure that we had before. So alpha minus is this quantity, alpha plus is this quantity. Well, they're both again of this same form here. Alpha is much, much less than 1. If we have r, this should be an s right here. r much greater than s. Well, we do the same thing. We form the series. This is the same series that I had before. We substitute in our alpha plus and alpha minus, and the only difference is they have s instead of d over 2. We form our positive series and our minus series. We put in our alpha plus and we put in our alpha minus, and we end up with these series here. And just as before, this quantity here is represented by this series, and this quantity here is represented by this series. And realize we could keep going in the series to get higher orders of s over r. Well, to form the 2 plus charge potential, this is what we're after, we just take those two series and we add them, realize they're both positive. That's this quantity right here. And we're going to throw out all terms that are smaller than 1 over r cubed. So for example, this, realize this r would come up here, so this is s squared over r cubed, and so on. So this would stay, this would go, this would go, this would go. So we're left with this expression right here. This expression right here is in fact the potential due to those two positive charges at this point here, the approximate value. Now we add the potential due to this charge, which is just k times 2q over r, with the minus sign because of the minus charge. Well, see what's going to happen is this 2 over r and this 2 over r are going to cancel, and so you're left with these two terms right here. So canceling those terms, we end up then with the full quadrupole potential of this particular quadrupole is equal to a quantity 2kqs squared divided by r cubed, and then times the Legendre polynomial right here. This is P2 right here. So one more point I want to make is that some of these moments depend on the coordinate system that you choose. So imagine that you have two coordinate systems that are just simply separated by a displacement vector a. So what that means is that your x-coordinates would be changed in the following way. This is the y hat, x hat coordinate system. So the x value will be equal to x plus ax. Y hat would be y plus ay, and so on. So let's look at the dipole moment in the hat system. So the p hat is equal to this quantity right here, the basic definition given a charge distribution. We'd be using r prime hat for that particular integral. So here's r prime hat coming from the origin of the hat system. The hat quantities are related to this translation by a. So r prime hat is equal to r prime minus a. So we can take this two terms and treat them separately. So the r prime term is here and the a term is here. Well, what you have here then is that this quantity right here is p. So it's the dipole moment in the xyz system. This right here is a constant, a, and this is the total charge in the charge distribution. We have this difference between the two dipole moments. This is in the hat system, this is in the xyz system, and they differ by this translation times the q. Well, if q is not equal to 0, then we would say that p depends on the coordinate system. If q is 0, then those are equal. So p does not depend on the coordinate system.